you look at Carol's career in the last 5 or 6 years, you'll see a lot of different administrative titles and positions she's had. She was the founding director of the
School of Energy Resources.
School of Energy Resources. We have SER and ENR and all these abbreviations, and I can never keep them straight. But she was the founding director of the School of Energy Resources just 6 years ago. But when I came on the campus 20 years ago, Carol already had a very strong reputation as a researcher. Even though I'm way over in the humanities and she's on the other side of the campus in the sciences, we knew that. We knew that. We knew that if we wanted a model of a powerful researcher, that Carol was one of the people to look at. And if you look at her history of research and publication, she's published over 100 articles on various geological and related issues, and water, of course, as well. Beyond that, Carol is an accomplished teacher. She has earned Extraordinary Merit Award in teaching. She's earned the Elbogen Meritorious Classroom Teaching Award. She's been voted a top 10 teacher. And just 2 years ago, she was awarded the George Duke Humphrey Award, which is UW's highest faculty honor for extraordinary teaching, scholarship, and service. And if you look at her teaching record, it includes a number of PhD students. Geology is one of our strongest doctoral programs in the university, as well as master's students. But it also includes courses like Geology 1000, Earth Science and Society, Geology 1100, Physical Geology, and Geology 2000, Foundations of Geology. So this powerful researcher, award-winning teacher is somebody who teaches our freshmen and our sophomores, as well as students all the way up to the top. And so with that, I want to introduce Carol Frost, who's going to talk about fingerprints on Wyoming's Rock of Ages.
Well, thank you, Paul, for inviting me to participate, and to all our local hosts, and also to all of you, because you know there's nothing you can do to make a teacher feel happier than to ask her to talk to you. So I have very warm feelings to you all. I'd like to start just by making a few comments about the title of this talk. When you see something that says Fingerprints on Wyoming's Rock of Ages, Clues to Growth of Continents, you know that I think about geology as detective work. Now, really, all scholarship is detective work, right? Say you're doing the social history of Jackson Hole. You're going to be trying to figure out what resources to identify, who to consult, who to talk to. It's the same thing with geology. Instead of interrogating and interviewing people, we're interrogating the rocks. Now, if we look at this picture, I guess I have to interrogate you. Where is this in Wyoming? Anybody know? This is the Sweetwater River. Devil's Gate, you got it. That's right. And this photo dates back to 1870, when the Hayden Survey was doing the first geologic mapping of Wyoming. Now, this picture doesn't turn out very well, but there's some people there. Little geologists trying to get fingerprints off the rocks. So as a professor, my job is to teach people how to read rocks, how to read the landscape. And in Wyoming, that is a very easy job, because all of us have this geologic context. We look out our windows and we see rocks. There are no plants. There's no dirt covering it up. When I go to talk in Kansas, it is difficult. But here, and of course in this corner of the state, you have the beautiful scenery of the Tetons and Yellowstone, but you don't have it all. In our corner down in Laramie, we've got the Snowy Range, and here I've got Red Canyon near Lander. And of course, our environment is really a part of us aesthetically, but it's also a part of our economic basis, because is the basis for our tourism industry and other things that deal with natural resources. But of course, the other aspect of Wyoming geology is the resource part, the energy piece. And we have it all again. Our natural gas production is one of the top in the nation. We produce more coal than anybody. I mean, we produce 40% of the nation's coal, don't we? If it weren't for our coal, we would have only 2/3 the number of light bulbs ignited in this country. Our oil and gas our oil industry is increasingly important. It's coming back up after many decades of decline, thanks to some of the condensate production that's associated with the natural gas in the Pinedale and Jonah fields. And then down here, I have a sycamore leaf. Why? That is a fossil that's found in the same formations as our Trona in southwestern Wyoming. So this is part of Wyoming that everybody knows, our environment and our energy. But something that's less well known about Wyoming geology is that our state has rocks that are some of the oldest in the world. And so when it comes to understanding how our planet evolved, how our continents formed, and how they evolve over time, we have an ideal natural laboratory. And it's that part of Wyoming's geology that I'd like to talk to you about today. Now, first we have to put ourselves in context. In this little inset map, you can see some pink and red colors. And those show you where the rocks in North America are that are older than 2.5 billion years in age. Those are the period of time, it's the period of time called the Archean. And you'll notice that Wyoming is there. And here in this blow-up map, here's the actual state boundary of Wyoming. And the yellow area is the area of Wyoming that's underlain by rocks that are 2.5 billion years in age. They may extend out under Idaho, but there's other stuff covering it up, so we can't really tell for sure. And although I have to confess, it really pains me that Laramie is right off the edge on younger rocks. Nevertheless, Wyoming is what I would like us all to think of as the nucleus of North America. We are the core around which everything else has developed. Now, the problem with studying rocks this old is that there is no fossil record of at least macro fossils that we can use to establish relative age and therefore the relative sequence of events. So we have to use natural radioactivity that occurs in rocks, and that's actually my specialty. When I first got to UW, and I have to tell you it was 1983, John McPhee had just published the book Rising from the Plains, and it's about Dave Love and his family. Dave, I know, is a friend of some of the people in this audience, and he went around with John McPhee describing the geology of the state. And in part of the early part of the book, there's a comment about Dave Love disparaging black box geologists. And he was talking about me. Because he thought that, you know, people like me that did a lot of lab analysis didn't really understand geology. So I would just like to set the story straight right now that I do a lot of field geology, and it is foundational to everything I do after the fact. So here, for example, here I am in the winds. This is pronghorn, trying to figure out how extensive a certain granite intrusion is. This picture is actually up Waterfalls Canyon here in the Tetons. And here my students and I are trying to figure out the origin of some light-colored rocks that I think are analogous to some of the granites in the Himalayas. And I'll tell you a little bit more about that later. I was looking at this photo this morning, and I noticed that I am doing the work, and the students are standing around. Yeah, well, so there are things you have to learn when you do field work, right? So here's one of my PhD students who's sampling coal bed methane-produced water impoundments. Here are a couple of the kids. These slides really don't show too well. In the Tetons here, this is up Osprey Canyon. And then here's a crew in the winds. Now, I have to tell you, they're smiling, but they shouldn't be. They had a lesson that morning. I say fieldworks educational. They put down my cafetiere coffee pot right next to the stove and melted a big hole in it. And I had no coffee. And the rule in my department is very well understood. No one's happy if Carol's not happy. So this was a very bad day. And here's another bad day. This is me in 1983. I grew up in Alaska, and I do know enough not to drive across muskeg. But I did not realize that Wyoming meadows can be dangerous. And here is the Suburban up to its axles in muck. And there I am trying to build the beginning of what about 5 hours later was a log corduroy road that the Romans would have been proud of. Okay, so presumably you do your good job out in the field and you understand the relationships between the rocks that you see, but to actually get quantitative information about what happened when, we need to use radioactive decay. So we have to look at elements that have a radioactive parent that produces daughter isotopes. If we count the number of parents that are left and the number of daughters that are formed, we can actually figure out how long the clock has been ticking because these isotopic parents have known decay rates. And there are two things that you can find out from this. And one I've already referred to, and that is the age, how long it has been that this clock has been ticking. And then the other kind of information you can get is about the origin of the rocks. I think of it as a fingerprint. So I'll give you some examples of each of these. But first, just some pictures of our lab at UW. As you can imagine, when you are getting out just a few nanograms of parent and daughter element, you cannot afford to have something drop out of the air into your sample. So the blanks or the contamination levels have to be down at the picogram level. So we're very careful to do all of our work in a class 100 clean room. This is of the standard that you'd have a lot of medical technology. Semiconductor chip factories have this kind of clean environment. We never have open samples. If we need to evaporate something, I don't just put it on a hot plate. I have the Teflon beaker under Teflon cups where I put heat down, blow clean air across to take the evaporate off. So at the end of the day, after some chemical separations, I end up with a very, very small, amount, you can't even see in the bottom of the beaker, of a parent and a daughter element. And then I need to weigh the number of atoms of each isotope, which is done in a mass spectrometer. So you basically shoot the ions toward a big old magnet. This magnet weighs half a ton. It tries to deflect the beams, and the beams are deflected more or less depending on their mass. A couple of observations about this bottom picture. First is I actually had some color in my hair when this was taken. And the other is this is our older mass spectrometer, which you can tell because it has a dinosaur on top of it. All right, so first, of the two things you can find out from radioactivity age and then origin, here's an example of dating of rocks. This is the Boulder Canyon granite. This is in it's on Loop Road in the Wind River Mountains. I think it's called Boulder Campsite. I don't know. So we took a sample of this granite. We extracted from it some of the minerals that have radioactive parents and daughters. The mineral we did for this one is called zircon. It contains uranium. You all know that uranium decays to lead. And so we take those grains, get out the uranium and the lead, and we're able to determine age quite simply, actually. So now here, let me just give you a little tutorial, because you know this, I think. There are two isotopes of uranium. One is uranium-235, and the other isotope is uranium-238. And they're both radioactive, so they both decay. Unfortunately, they decay to different daughters. The uranium-235, after about 1 billion years, half of it will have converted to 207 lead. For uranium-238, it decays more slowly, so it takes about 4.5 billion years before half of it will be 206 lead. So you can see that if you start with a mineral that has uranium in it, but no lead, then you'll start somewhere at 0, and the older the mineral gets, the bigger this number will get, and the bigger this number will get. And so the older the rock is, or the mineral is, the farther up this red line, where the two ages are concordant, will be. And we know what age this is: 2.56 billion, this is 2.6 billion. And here are our analyses. We can draw a line through to the intersection and see that this particular rock is 2.6295 billion years old. And the uncertainty is 1.5 million years. That's pretty good, right? I actually learned this in Switzerland, where they're very fussy about this kind of thing. And in fact, the man I worked with had been to this very place as a postdoc when he was at Caltech. And being a good Swiss person, he'd had all of his army experience, and so he used dynamite to get his sample. But his uncertainty was plus or minus 13 million years. So we're quite good at UW. Okay, now the other thing you can do with natural radioactivity in rocks and other earth materials is figure out where things came from, what are their origins. And for this, I'd like to use the example of some of the work my students and I have done in the Powder River Basin on the produced water associated with coal bed natural gas. Here's one of our students collecting water from one of the outfalls that actually goes into a holding pond. And we collected samples from many, many different coal seams from these CBM wells. We also sampled water from various sandstone aquifers that are either above or below the coals. And in this case, the analysis that I'm showing here is the isotopic composition of strontium. And strontium, if you remember your chemistry, is in the same column with calcium. Calcium is very common and commonly dissolved in water, so there's also a little bit of strontium in water. It's totally inert, really, except the strontium-87 is a daughter product from decay of an isotope of rubidium. So if the water's been in contact with rocks that have a lot of rubidium that's decayed to strontium, then that water will dissolve strontium that has a high ratio. If the water is going through rocks with very little rubidium or very young rocks, they'll have a low ratio. And what we see on this diagram then, I've plotted the isotopic ratio that we measure, and just for interest's sake, the error is 1 in the 5th decimal place on these analyses, so the error is much smaller than these spots. And I plotted the sample as a function of how far away from the edge of the coal outcrop it is. So if you think of the Powder River Basin, and you think of all those big coal mines on the east side of the basin, we're looking how far in are some of these CBM wells into the basin. When you look at water from sandstone aquifers in the Powder River Basin, they are all dissolving the calcite cement. They all have the same isotopic ratio. So you can tell if you're pulling water out of a sandstone. If you pull water out of coal seams, it does depend on where you are. It seems as though when the water first recharges into the coal, there's a little bit of strontium, but the longer the water stays in the coal, the more it interacts with that coal and picks up strontium that has a higher and higher ratio. And so if, for instance, you're concerned that you don't want to produce unnecessary amounts of water as you're recovering coal bed methane, you don't want to get water out of anything but coal, right? I mean, if you're pulling it out of adjacent sands, you're wasting that resource. So you can use the strontium isotope ratio to tell. And I'll just give you an example. Here's a spot over here you've been looking at already, right? You're thinking, what is she telling me? Because here's a blue spot over here. Well, I thought the same thing. So as soon as I did this analysis, I went next door to the survey, the geological survey, and pulled out the well record, the drilling record. And this company had drilled down to the top of the first coal seam and cased down to that point. And then they had an open hole that went through about 50 feet of sand, through another coal, and then 20 feet beyond that into the shale and sand below. So this well was open not just to water in the coal seam, it was pulling out water from the sandstones as well. So this is an example of a well that isn't being conserving of our water resource. Okay. And I'll just give you one other example of the origin thing because it's a little less intuitive than age. This is also about the Powder River Basin. I had a couple of students who agreed to take a tour with me from near Casper at the headwaters of the Powder River all the way down to its confluence with the Yellowstone in Montana. And we did this in the spring and the fall for a couple of years. And of course in the spring there's a lot of meltwater and there's a lot of water in the river, and it's actually kind of a pain to have to go sample the water in the middle of the river. And then in the fall there's almost nothing going through. And what we did was we analyzed the water's carbon isotope composition. Why? Because the Powder River Basin coal bed methane is biogenic. It's made by bacteria. And when they munch the coal, they preferentially take up a light isotope of carbon, and they leave behind in the water the heavy isotope. So here, for instance, are two tributaries to the Powder River that have almost nothing in them but produced water discharge. These are ephemeral streams that are now full-time flowing because they have all this discharged water. And you can see that the carbon isotope ratio, which has this delta notation, is positive. If you go way to the headwaters of the Powder River, way upstream of any coal bed methane producing areas, the water is negative. And that's normal. So what we discovered was that carbon isotopes are a really sensitive indicator of whether produced water has gotten into the main stem of the Powder River. Why do we care? Well, you know why we care, right? Because Montana was very concerned that we were degrading the quality of water that they depended upon for irrigation when it got up into here. So what this is able to show us is as we go from the headwaters of the Powder River downstream, here we are about at Sussex, the water in the Powder River at low flow is the solid line, becomes positive. That means there is produced water in the Powder River. But here's the state line, and it goes right down into Montana. And why does that happen? It's because there are some major tributaries like Clear Creek that come in that don't have any produced water and basically dilute that signal. So I actually have a crack PhD student who's doing some very sophisticated Bayesian statistical analysis, and he can tell you exactly how much water is in the Powder River from coal bed methane produced water when it gets to the state boundary there. And we can also show that it has no impact on the constituents of concern for agriculture, the SAR, and the total TDS. Okay, so those are my two examples. Now we have to do the corny part of the talk. All right, somebody was talking at dinner about how they love the Wyoming road signs that say, these rocks are 400 million years old. I love them too. But, as somebody was saying last night, you know, there's this sign that says 3.1 billion years. I just can't even conceive of that. And it's true. That's so far beyond our comprehension that we have to do something to make some kind of analogy. So what I'm going to do is ask you to pretend that I'm 46, because the Earth is 4.6 billion years old. And if we say I'm 46, then I can have each one of my years represent 100 million Earth years. And you all remember from high school English about willing suspension of disbelief, right? Okay, so we can look at the history of Wyoming in terms of a human life, and it actually doesn't work too badly. So if we take our first little chunk of time, we'll take the period of birth to 12 years. And That would be getting us up to about 3 billion years ago. Now, I don't know about you, but if I try to think back to my earliest memories, they're fairly obscure, right? You know, you might have some fuzzy recollection and you're not really sure whether it's your parents' video that you remember watching or whether it really is your own memory. Well, that's the way it is with trying to identify the earliest part of Wyoming's history. Everything has been overprinted and overlain by so many subsequent events that it's hard to see back to the beginning. Now that said, if we look at this map, again where we're looking at the Wyoming province, remember, nucleus of North America, it's the area in blue that has the very oldest rocks. And unfortunately does not include you or me. Now, in most parts of this blue area, even here, these old rocks have been seriously overprinted by subsequent events. The most pristine old rocks are found along in here. What I'm showing you in these bottom pictures are some of the grains of the mineral zircon that I took from a gneiss from Powder River Pass in the Bighorn Mountains. And there are two kinds. This is a cathodoluminescence view of a really big pale pink grain. And when I did the dating on that, it turns out to be 3 billion plus or minus 20 million years. And this is not the age of the rock. This is the age of a grain that magma picked up as it went through the crust. So this is telling us about the age of rocks underneath the granites and gneisses in the Bighorn Mountains. We can also find that kind of history out by looking at complicated grains. So here's another grain of zircon, and I don't know if you can kind of see there's a round part here in the middle of the grain. So we actually can analyze just the middle, and the core of this grain is 3.25 billion years, plus or minus 10 million. The outside is 2.9, which is the age of the main massive magma. So very, very fuzzy early memories of Wyoming, but really interesting and really some of the best places, most accessible places in the world to study old rocks. Another way we can get back at the old history is by looking at sedimentary rocks. And what I have here are some analyses from quartzite. This originally would have been a sand, a quartz-rich sand. And along with quartz grains are some of these zircon mineral grains as well. And I can zap up to 100 or so grains from these quartzites, which may have been deposited relatively recently, but what the ages of the minerals tell us are about how old the rocks were that eroded and provided all this detritus that accumulated in the quartzites. And you can see this location in South Pass, near where the reclaimed iron mine is. All these individual spots show that the rocks that eroded to give the material that's in this quartzite are 3.3 billion years or older. And the same with this sample here in the Granite Mountains, north of the Sweetwater River. Again, 3.3 billion year old grains. So that tells us there was a lot going on that we really can't see very clearly, just like when we think of our own early days, we can't see and remember that very clearly. Okay, now if we take the next block of time, let's take the equivalent of the human age of 12 to 15. And what happens when you have 12 to 15-year-olds in your house? There is no food, right? That is a time when these kids are growing like gangbusters. And the same thing was happening to Wyoming. We had this blue area with the old rocks. And in this interval, we added on all this material. And I'd like to start with the yellow area because this is your area. We have, one of my active NSF grants is in the backcountry of the Tetons. The Tetons are wonderful. They're kind of a paradox because they are Wyoming's youngest mountains. That is that they have been lifted up relative to Jackson Hole very recently. But when you walk back in and look at the rocks, we're looking at some very old rocks. So we wouldn't be able to see those rocks if it weren't that the mountains had been brought up and then eroded away. And the geologists in the audience might recognize this as kyanite. This is the mineral kyanite. This only forms at high pressures. So by looking at the kinds of minerals that are formed and some of the compositions of those minerals, we can figure out how deep these rocks were in the past. This rock started its life as a mud. So it started on the Earth's surface. These minerals tell us that it was at one point 20 miles down under the Earth's surface. The only modern place where we see crust continental rocks that have gotten jammed that far down are when two continents collide, like in the Himalayas. So very, very interestingly, the Tetons expose what turns out to be the oldest known continent-continent collision in the world. It's kind of a secret because we've only just figured this out. But it is extremely, extremely cool. So that's one of the ways that Wyoming grew during this period, is by different blocks crashing together and being glued together, just like India crashed into Asia. Now, there are other ways that continents can become more massive. One way is just like people. People can grow up and they can grow out, right? So continents can grow by accreting stuff to their margins, but they can also grow kind of by inflating, by magmas being intruded from below. And so when you look next time in the Wind River Mountains, like here's Warren, in much of the granite mountains, they're made of granite, surprisingly, huh? Those all formed big, big batholiths of magma solidified in this period of 2.8 to 2.5 billion years ago. And then finally, in this light blue area, at this time, we had lots of volcanoes and oceanic rock get jammed up against the side of the Wyoming Craton. What you need to think of, perhaps, is Indonesia, where there are lots and lots of islands and arcs. And as Australia moves north, those are going to get smashed up against Asia. That kind of process happened 2.5 billion years ago in Wyoming, and all this material accreted at that time. I've tried to kind of show it here, where the orange is the old part of Wyoming, and we have batholiths, magmas intruding into it, but we also had pieces stuck up against it and even thrust up on top. So it was a great period of expansion of the area that is now the Wyoming province. All right, now this gets more and more corny as I go along. I really have to apologize. But something really, really, well, I was going to say sad happened to Wyoming about 2 billion years ago, and that is part of it disappeared. This is the Snowy Range, and again, I'm sorry, these photos are so dark, but if you can imagine Medicine Bow Peak, you may have in mind a pretty light gray to white rock. And that is a sandstone that's metamorphosed to quartzite. And it was deposited about 2 billion years ago. So if you had climbed Medicine Bow Peak, well, if you'd walked onto the area that's now Medicine Bow Peak 2 billion years ago, you would have been sitting on a sandy beach. And if you looked south, you'd be looking at the ocean. There would be no Colorado. So this is a time when whatever was south went away. And we can see both the beach sands that are left, and also we have, I'm so sorry you can't see it, there's some black stripes that run across the face of these cliffs, you all may remember. Those are magma-filled cracks, and those also indicate that the rocks were rifting apart. So if we were to try to use our human analogy, then this is the age when you leave home, right? Now, it doesn't last long because you wouldn't have been able to sit on the top of Medicine Bow Peak and look at the ocean and maybe a few volcanoes where Colorado is for too many hundreds of million years, because by about 1.76 billion years, lots of things had come crashing into the southern part of Wyoming. And that's the time when a lot of proto-North America was assembled. In fact, all this area kind of got all put together at about this time. And so this I really hesitate to say this. This is sort of like, you know, getting married or something. It's a time of great amalgamation. Now, thankfully, you know, we tend to grow up. Well, maybe I don't, but later on in Wyoming's history, very little happened. So here I'd like to just focus on the period of about 1.44 billion years ago, when a lot was happening around Wyoming. All the orange in these, on this map indicates activity at about this time. Of course, we can only look for it in places where rocks that age or older are exposed. But there were big sedimentary basins being deposited up in Montana. There are lots and lots of intrusions throughout southwestern US, but very little happening in Wyoming. And the reason is because by this time, it appears that Wyoming had become so stable and so strong that very little could happen. And the only thing we find are, again, some dikes that come up through cracks, including potentially the dike on the face of Moran. We don't really know. We've never been able to date that. But that's the kind of feature I'm talking about. There are some dikes like that in the Wind Rivers and the Granite Mountains, but nothing else. It was a time of very stable kind of maturity. Now, I would like to talk to you a little bit about the activity happening right here in southwest Wyoming, because that was on the edge of the craton at the time, and there's some pretty interesting things that did happen there. Two kinds of rocks that are very dissimilar. The first is called a northocite, and it's a rock that's composed almost entirely of just the mineral plagioclase, which is a feldspar. If you go on the road from Wheatland to Bosler, through Sabile Canyon, next time you go, don't think, oh, they're just boring gray rocks. Because these rocks, it turns out, are the closest analogs to the rocks on the highlands of the moon of anywhere on Earth. These actually, most of the anorthosite on Earth is metamorphosed and deformed. These are pristine. And in fact, some of the crystals have the composition that give a beautiful schiller or play of colors. It's just gorgeous material. And it was when I realized this that I finally understood one of our Wyoming Tourism Department's slogans. Do you remember back when our slogan was, "Like no place on earth"? Now, you know, if you're thinking of Sabile Canyon here, you go just a little bit south and you have Vitavu. And these are rocks that are made almost entirely of a different feldspar. It has potassium instead of calcium and sodium. Very unusual juxtaposition. But the interesting thing about these rocks, again, they're 1.4 billion years, and my group studied these quite extensively. They have the composition that is a dead ringer for the magma that's beneath Yellowstone. Okay, it's quite unusual, very iron rich. And so if you were to come back to Yellowstone, after all that magmatic activity had ceased, all the magmas had solidified, and the rocks had eroded down, you would see rocks that look like this. So I refer to the Sherman granite at Vitavu as Yellowstone underground. Okay, now the next thing is, I was going to say nothing, but that's not right. We have no record of the geologic events that happened in Wyoming from 1.4 billion years to 500 million years ago. Now that corresponds to the human age of 26 to 40. I came to the university at age 26. The next thing I knew, I was 40, and I am sure things happened. And it's the same with the rocks. There were things that happened probably all kinds of things happened. It's just that all the evidence is erased. And you know, actually in this part of the world, you are missing the record from about 2.5 billion years to about 500 million years. You know, if you go into the Tetons, you're going off of, well, look at Mount Moran again. You've got the set, remember the little sandstone on top? That's about roughly 500 million years, and the rocks it's sitting on are 2.5 billion years. So you're missing 2 billion years of Earth history in that little boundary there. Okay, so it's kind of interesting to think about a lack of a record. But after that, we have all kinds of detail. And this is just like how you could tell me what you bought at the store yesterday, what you ate for breakfast, you know, what vacation you went on last year. We can read a whole lot into the geologic history of Wyoming once we get to about 500 million years ago. And that's, of course, where the fossil record really becomes important and significant as well. So this is where I sort of say, well, from here on out, we're just rearranging the deck chairs. But that isn't fair, because there's a lot of really important things that happen in this most recent period of Earth history that control our natural resources. So for instance, the rocks that are right on top of the old rocks are sandstones and limestones that form many of our most important water and oil and gas reservoirs. After these were deposited, we know there was an older Rocky Mountain uplifting because these rocks have disappeared from the areas that became mountains at that time. They were eroded away. And then after that, we have a lot of our important geology, including the formations that host our dinosaurs. When what we think of as the real Rocky Mountains came up, those are the ones we see today. They formed the basins in between the mountain ranges where we have many of our resources. For example, as the Bighorns and the Black Hills were being lifted up, we had a basin that's now the Powder River Basin form. And that basin was inland. It was not connected to the ocean. So the coals that form there have low sulfur because the source of sulfur in coal is from marine seawater. So that's part of the reason why our coals are so highly valued, is that ours are fresh water. And that's a direct reflection of our geology. Another thing that happened during this time when the current Rocky Mountains were uplifted was that we formed structures that are great traps for various things. And the example I'm using here is traps for potentially sequestering carbon dioxide if we need to do that. So here we're looking at southwestern Wyoming. I often think southwestern Wyoming doesn't get a real fair shake because it's not as scenic as much of the rest of the state, but actually it hosts some amazing resources. And so if we went from along a cross-section from here to here across the Green River Basin, and we look at the geology, you can see this is enormously magnified by about 15 times. But you see that in addition to things like the Wind River Mountains being formed, we have what would be mountain ranges if we didn't have so much stuff covering them up. And so we have these structures that are kind of cup-shaped that actually become traps. Here's the Moxa Arch, and this is the structure that traps the gas on the LaBarge platform that is it's sour gas that's refined at Chute Creek. And then here's another cup-shaped formation at the Rock Springs Uplift. And so these are the kinds of places where if we look at the sandstones and the carbonates that have a lot of suitable porosity, that's where we'd want to put carbon dioxide underground because it'd be trapped at the crest of that dome shape. I talked a little bit about the coal formed in the basins as the Rocky Mountains come up, and the same thing was happening with the Trona down in southwestern Wyoming. This is also the time when a lot of the uranium that had originally been in the old granite rocks of Wyoming was mobilized, dissolved, and deposited in the basins and form the basis for our uranium reserves. And finally, most recently, of course, especially in this corner of the state, we have active geology. And so the string of volcanoes that goes across the Snake River Plain end up in Yellowstone Park, give us our thermal features and some of the big catastrophic eruptions of, I'll remind you, the same composition, magma and ash, as at Vitavu. Well, so that's the tour of Wyoming Geology, and I think you can see that it's a story that I really love sharing with students. And for all of our environmental and economic resources, of course, our students, our people, are worth a whole lot more. And so really what matters isn't the details of what I've shared with you, but the fact that at a university, we have really an amazing opportunity to engage in inquiry. You know, we get to try to identify what are the important problems, how do we define them in a way that we can solve them. And that is really what is fun for me and why I feel like I've had such a wonderful career. It doesn't really stop with the students. Whenever we have a problem in this state, it seems like we try to get together. Like when I was trying to build our carbon sequestration program, there were a lot of holes that we just couldn't fill at UW. But state agency heads were willing to come and sit down with me and figure out, okay, who knows these things that we don't know? And I remember one of them saying, Carol, this is a small state. We don't even have enough people to run a state. But the flip side of that is that it means every single one of us has an opportunity to help run this state. And I think that's what's really, really the most important thing. And it's one of the reasons why I think even though we may be down in the other corner of the state in Laramie, we really do feel a part of the community that extends all the way here. And with that, I'll just say, and that's why I really appreciate getting a chance to come and talk to you today.
For questions, so if you want to direct your questions to Carol.
What are some of the theories regarding the missing 2 billion years?
Well, you're asking about things for which there's no evidence, you know, and so the question is, what happened? Well, probably a lot of the same kind of processes that happened before and after, volcanism, sedimentation, but I can't even speculate because I'm a scientist and I need data, and there isn't any. So I'm sorry. Where did it go? Well, what happens is, of course, things get eroded away and deposited somewhere else. So you can imagine, for instance, what if we came back and the Tetons had been completely eroded away? We wouldn't know what was there. We wouldn't know how old it was. We wouldn't know all the events that had occurred. That's the kind of thing we're talking about. Yeah, it probably is in the Gulf of Mexico, actually. Yeah.
Carol, your expertise on water quality in the Powder River Basin, I am concerned. I know that this movie Gasland, that's
Oh, right, yeah.
Is one of the best documentary. Would have us believe that water quality is really endangered with hydraulic fracking that they're considering doing in the upper Hobart River Basin.
Right.
Do you have an opinion? Is it safe? Is it not safe? What is your research?
Yeah. The question is really about the whole issue of fracking and how environmentally safe is that. And you know, this is, and you mentioned the film Gasland, and this actually makes a connection with Gracie, because I was thinking as I was listening to your talk, Gracie, how scary that opening video was, that you might actually be fed news that was just what you were interested in knowing, and how that further fractures our common understanding of our human experience. You know, we all used to watch Walter Cronkite. We all knew what he told us. We're now in an environment where it gets harder and harder to evaluate the validity of some of these claims. I don't think it's ever a good idea to do something experimental to a natural system without being pretty careful about the potential consequences. And so I think everybody's wise to ask questions about fracking. What are they putting down? Where is it going? How deep is it? Because we have had bad experiences. Many people don't know that in the Powder River Basin, those coal bed methane wells are fracked, but they're fracked with water. So they're just using the water they pump out to pump back in and kind of fracture up and clean out the area around the base of the well. And so the first question is, what are they putting down? If it's just water and sand to prop open the cracks, that's probably one thing. But if they're organic materials, how are they going to react with the water down there? So those are one class of questions that I would want to ask. The second is how deep and where is the fracking going with respect to where the groundwater supplies are? Are they below all U.S. drinking water aquifers, which are defined federally for us? How well are they cased? And the other thing is, of course, the idea behind fracking is that you put this material in, crack open the rock, and then you bring the material back out again. The intent is not to leave it down there or to have it fracture into areas that are susceptible in any way to damage. Of course, the concept and the execution can be two different things. So I think, I'm not an expert in this area, but I think it's possible to do it safely, but I think it's always our job to ask those questions. Yes?
I was interested in your analysis you did on rocks, your chemical analysis. And I had a question about, I'm sure you're aware of the quartzite gravel in Jackson Hole over in the Wind River Mountains. They've been eroded very roundly. They're extremely hard rock. I'm wondering if you did has anybody done any analysis on that, what the age of those are, or where they could possibly have come from? They're very, very hard. Very rounded. They've been transported quite a ways by water or something.
I don't know the answer.
Okay.
But I could try to find out.
Thank you.
Yes?
You started with uranium, and my question is, on the aging, is all uranium start from one point, beginning of the Earth or something like that, and does that mean that no new uranium is created? It's all whatever you started with at the beginning?
Yeah, you're right. Where did all the uranium come from? Well, in introductory geochemistry class, I always like to say, look at your hands, you're made of stardust. It's because all the elements are formed in stars or through the explosion of stars. All that material got swept up into different planetary systems, including our Earth. So when the Earth formed, we had a certain budget of uranium. And you're right, it's just been decaying away ever since, and no new uranium is formed. Mm-hmm.
Recently, there's been a lot of discussion about exploitation of rare earth minerals and how China controls a lot of that. And I think I saw an article a couple weeks ago about maybe some of that going on in northeastern Wyoming or Montana. Can you talk
That's
about
right.
that a little bit?
Yeah. So rare earth elements actually include some of the radioactive parent isotopes that I study. My favorite one is neodymium, which decays to samarium. Rare earth elements really aren't very rare, but they're usually dispersed in very small quantities everywhere. And it's pretty rare for them to be concentrated. But the one kind of rock that does tend to have high rare earth contents come up in magma pipes or diatremes. And there are a set of these that run basically from the northern Black Hills across Montana. And so near Sundance, near Devil's Tower, there are some of these diatremes that are being prospected for their rare earth potential. And they definitely have high quantities of rare earth, but it's always a question of is it economic? But that's where it's happening. And you're right, as the Chinese tend to tighten up on their exports, then the economics are going to be changing in favor of recovering from areas like that. Yes.
guess this is a pretty basic question, but what is the origin of the hydrocarbon deposits in various seas?
Well, it's organic matter. And the kind of organic matter varies and tends to make different kinds of deposits. So it's mainly marine microorganisms that provide the organic matter that becomes oil. And it's generally woody plants that become the precursors for coal. And then natural gas can be formed by two processes, either by little critters munching on organic matter and making a biogenic gas, or you can take organic matter and just heat it up and crack the complex long chains apart into short enough chains that they're gas. So really, we have the whole spectrum here in Wyoming. Good question.
You talked about Wyoming, I think about age 19 or 20, being formed out of the conjunction of a couple of plates. Now, does that mean that the sort of North American continental plate that we saw in sort of our high school geology books is actually a complex of more than one plate? Could you?
You're right that what you get in your textbooks today are the current plates and their plate boundaries. But as these move around, they change shape and size, and the plates that have continents on them themselves have been built up by a series of stages, just like we were talking about for just Wyoming. Yes?
What's Trona?
Don't ask me to give you the chemical formula because it's long and messy. Trona is a mineral that forms by evaporation. So if you think of the Bonneville Salt Flats or Death Valley, where you've got just very shallow, briny water that evaporates, or even the Mediterranean Sea, it totally dried up about 4 million years ago and made these thick salt deposits. Trona is one of those minerals that forms by evaporation of lakes. And the reason it's associated in Wyoming with the fossil fish is, you can imagine, as the lake dries up and gets really salty, the fish are going to die. So you get both dead fish and Trona. Yeah. Okay, well, on that oh no, we have one more? Yes, please.
Is this measure of rock similar to the states around here, and is it very similar or dissimilar to the East Coast?
Oh boy. You know, I'm teaching physical geology in the fall, and I'd be happy to have you take it. You know, I think you can find similarities in rocks of all ages in all places, and that kind of goes back to the basic philosophy of geology, that the present is the key to the past, that somewhere today there's something going on that's like what has happened in the past. And so we can take that pretty much anywhere we want and say, at one point, mountains were being built up, the Appalachians, by continent-continent collision, just like the Tetons were formed 2 billion years previous. So it's very interesting because processes are commonalities globally. Okay, and on that philosophical note, I should probably be quiet, right?
Thank you
yes.
very much.